Welcome to session 16 on combined loadings. In this session, we are going to have the opportunity to think about how different loads that we apply to structures result in normal stresses and shear stresses that can be superposed on each other. So we'll first have a review on the different types of loadings and what superposition is in the first portion of this session. We'll then talk about the superposition of normal loads. And what we're talking about here are essentially normal axial stresses that we have in our structure that we can superpose or add to each other. In part 3, we'll look at shear stresses that we can superpose or add to each other. And you notice for this diagram that we have here, the load is actually an axial force, but there are resulting shear stresses that we superpose on each other. And the fourth part will be when we do superposition of normal and shear loads. So we'll be looking at normal stresses and shear stresses and coming up with the state of stress on a given element in the structure. So as a review, we have covered different types of loading, and I think we're pretty familiar with this one, which involves a normal force or an axial load on a bar, and the normal stress is equal to sigma, or we signify it as sigma, and we say it's P over A. We've also talked quite a bit about shear force, and we talked about single shear and double shear, and we talked about how when you shrink or make the beam less long, that essentially can be modeled as situations of a single shear or double shear. For the most part, we'll be considering the shear forces that we have internally in beams and the resulting transverse shear stress that we get on elements of a face or a selected slice. We have discussed bending moments, and those result in normal stresses that are given by the distance from the neutral axis and a second moment of area and the moment. We've also discussed shear stress due to twisting or from a torsional moment being applied to the system, or torque, and that is given by the torque times the distance from the center of the cylinder. In this case, we'd be looking at cylindrical shafts divided by the polar moment of inertia or polar moment of area. And the final kind of set of stresses that we've looked at has to do with pressurized thin-walled vessels. So we've talked about how we can have a hoop stress in a cylindrical pressure vessel, and we've also talked about how we can have this longitudinal stress, or half of the hoop stress, with PR over 2T in the longitudinal direction, the axial direction of a cylindrical pressure vessel, or when we're describing the stress in a thin wall of a spherical pressure vessel as well. Okay. Now, if you go back all the way to our first introductory session, we said some interesting things. Well, I thought they were interesting, and I just wanted to take a moment to show that we now have a better physical grip on why some of the things we presented very early on are in fact true. So for example, we had talked about the scaling of safely supportable loads in a bar that's axially loaded. And we said this supportable load is going to scale with the square of the diameter. And we said that it would scale with the cross-sectional area. Okay, that's the same thing essentially. And we also talked about how the length will not affect supportable forces unless, well, we haven't talked about buckling yet, unless the bar buckles. we now know, of course, that the length of the bar makes a difference in terms of the effective stiffness of that bar, right? The EA over L. But going to this point right here about the supportable load scaling with diameter squared, we now know that sigma is equal to this axial force divided by area, and that needs to be less than a yield strength for the material. Okay, so this supportable load, yes, it does scale with the area. If we increase the area, we're going to be able to increase the amount of supportable load that we can handle before we get to a point where we're hitting the yield strength. We also early on discussed torsional loading of a shaft, and we said kind of this interesting bit here that the supportable load is going to scale with the diameter cubed or with area to the 3/2. Well, we now know that if we apply a torque, and we can calculate out what the shear stress is, and that's going to need to be less than some shear strength of the material, and the shear stress is Tc over J. What is J? J is pi over 2, c to the 4th, and we do one more bit of math, and we see that the maximum shear stress that we can support is going to be 2 times this applied torque over pi c cubed. And look, we said that early on, we said the supportable load would scale with the diameter cubed, or area to 3/2. And that's what we see here, okay? That this value for the shear stress needs to be less than a shear strength. We also discussed in the first session when we met the transverse loading of a beam. And we said a few things. We said the supportable load will scale with h squared. The supportable load will scale with b. And the supportable load will scale with 1 over L. Okay. What do we know? Well, we now know that sigma is equal to negative my over I. And in this case, we're looking at maximum bending moment at the wall, which would be equal to FL, right? That's the M. The Y is going to be the H over 2, and the I is the BH cubed over 12. So we can rewrite sigma max as this quantity, FL, H over 2, BH cubed over 12, which comes out to being that 6FL over BH squared is the maximum bending stress that we expect. That needs to be less than our yield strength of the material. And if we look over to the left where we were describing the supportable loads that we could, and how they scaled initially, we said that supportable load, let's say F, would scale with h squared. Well, look, h squared is in the denominator. It scales with b. Look, if we increase b, we can increase the amount of supportable stress that we're going to have. And we said that, okay, so these two, right? And we also said that the supportable load would scale with 1 over L. And that's going to be dictated by here, right? So if we were to shrink L, or put 1 over it, or however you want to, well, not however you want to look at it, but as dictated by this equation, the amount that we're able to support is going to scale inversely with the length, okay, if we have a given F. So we were telling the truth, okay, in the very beginning of the class, and now we have the mathematical and physical relationships in our toolkit to be able to back up these initial statements. We also, early on in the course, discussed superposition. So in that case, we were saying, look, if I have one force, and it gives me some displacement, and then I have another force, it gives me some displacement, I could add these two displacements to each other, as we see here. So the net response would be caused by 2 or more stimuli is the sum of the responses. Well, now we're going to look at how superposing these different loads on a system affects stress. We're not going to discuss displacement too much today. besides what we just showed, actually. We're going to be discussing how the loads, the normal loads, can result in normal stresses, which we can add together. And we are going to discuss how the shear stresses can add up and come up with a kind of like a composite or superposed shear stress to describe the state of stress on a given element. We're going to make some assumptions here, and these are kind of for your good to know file, and Hibbeler goes through these assumptions and a procedure. But really, the heart of what we're doing is going to come out in the examples that we show. So first, material is homogeneous. Material has a linear elastic modulus, and the deformations are small. These are kind of familiar assumptions that we've been using before. Now, this procedure, I'll have it multiple times, and there are a lot of words here, okay? But there is powerful insight that can be gained from using this procedure. So we've heard this before. We're going to section the material, okay? And we're going to section it perpendicular to axis, okay, at point of desired stress. So often we're going to be taking a slice of a bar or a beam or a shaft, okay? And it's going to be like cut perpendicular to the axis, kind of the length axis usually. And then we're going to determine the normal and shear force components acting on that slice. And we might also look at the bending and torsional moment components. And the forces are supposed to be acting through the centroids, and moments should act about centroids. Okay. I don't keep all these words exactly in my mind. Okay. But essentially the point is, let's take a look at that slice. Let's look at what the forces and the moments and the torques might be on that slice. And then we're going to figure out what the normal and shear stresses associated with these different types of loads are. And so we're going to be looking at the kind of normal stresses, due to normal force, shear stresses due to kind of a shear force, or, again, we could have some type of point load force that twists and causes us to see some type of torque, okay, which could result in a shear stress. Okay, and this will become more clear as we go through the examples. Okay, I assure you. And we have to be very careful, because normally we say, hey, when we do equilibrium, keep track of the forces and keep track of the moments, and those are where you're going to add together. Well, on a given element, if we have a normal stress acting in the appropriate direction, same direction on an element, and we have another normal stress acting in the same direction on that element, we can actually add them together. Okay, we have to be very careful when we do this. When we talk about transformations, it'll become clear why we have to be very careful about this. But if they're acting in the same direction, acting at the same location, we can add them to each other. Same thing for the shear components or the shear stresses. Okay, and then we're going to show the resulting state of stress. So given what we've talked about and maybe some common sense, here is the first question associated with this session, with portion 1. It's like some of the exams you've probably seen. Yes, it's one question, but there are multiple parts here. Okay, so take a few minutes, answer them, and come back for the second part. Thank you.